Now I am going to discuss a very important topic under process capability analysis, and this is the last topic I am going to discuss, but it's a very important topic. And first I should mention what are the specific topics I am going to discuss, like related to measurement system. I am going to discuss its capability and the corresponding analysis. Concepts of measurement error or the gauge variability. I am going to discuss gauge variability and the total variability. How do you relate the gauge variability or the measurement error with the total variability? The so-called precision to tolerance ratio is referred to as the P&T ratio. What is it? We are going to discuss measurement of repeatability and reproducibility. Okay, in explaining the total variability or say total variability in the gauge, or say the gauge repeatability or the gauge variability. Now we refer to two kinds of variability, that is repeatability, due to repeatability and due to reproducibility. Components of the measurement error we will be focusing on, and we will be definitely discussing how to estimate the measurement system's capability. So these are the broad issues we will be discussing. Now related to measurement system capability analysis, a few points I like to highlight at this stage. Like we have been saying that for carrying out any exercise on quality, you need data. Okay, and once you collect data, you go for data analysis using certain tools and techniques, relevance tools and techniques, and then you conclude about the status of quality related to a particular process or related to a particular product or a system. Now obviously for collecting data, many a time majority of the time you need to use certain measuring instruments and or the gauges. Sometimes they are also referred to as the gauges. So ultimately, the quality of data is very much dependent on the quality of the measuring instrument. So that's why sometimes we make a statement that the quality is as good. If you recollect in the other lectures, I have mentioned this point, that quality is as good as the measuring instrument. That means there cannot be any situations where you do not look into the quality of the measuring instruments. You have been always looking into the quality of the processes you deal with, and you expect very good quality output. Is it okay? So when we talk about the process capability, that is one part. Now the process capability is definitely dependent on the measurement systems capability. Now why measurement systems? Because by using the measurement systems, you establish your inspection system. So if the inspection system quality is poor, it's not at all dependable, obviously it will have an adverse effect on the quality of the process, or say the conclusions you draw from the process performance analysis. There could be misleading conclusions too. So, and if you have misleading conclusions regarding the process performance, the implications could be very, very expensive, and the company may have to pay heavy price for this one. There are many such instances. So these particular situations you to avoid. So whenever you discuss process capability analysis, this discussion remains incomplete if you do not discuss the measurement systems capability. Okay, so I think in the context in which this particular topic is being discussed is now made very, very clear. For process capability analysis, some of the important points let me go through, which I have written. For process capability analysis, data collection is done with measuring instruments and gauges. That is point number one. You cannot avoid using say measuring instruments. It is essential that the measurement system must have a high level of capability. Capability means the same definition, ability to produce as per the specification. So here the definition is ability to produce as per as per the requirements. That means supposing to what extent you are able to measure a particular say dimension. Suppose it is 20.5, okay, the true value. Now are you getting 20.5 with your measuring instrument, or you are getting 20 or 19.5 or 20.8? Okay, so is there any substantial the difference? So to what extent it is unavoidable, to what extent it is avoidable, to what extent the measurement system or the measuring instruments quality is affecting this one. Like when, if you remember, I have mentioned related to measuring instruments, when you start using the measuring instruments, three important aspects you must be bothering about. The first one is definitely the precision. So you must know what is the precision level of the measuring instruments at a point in time. The second one is the accuracy, and the third one is the resolution. So you just go back to these three types of concepts whenever you start using a particular measuring instruments. So you must have your ideas, you must be able to measure all these three aspects or three features of a measuring instruments. So these are the preconditions. Now what do you try to do? That means you create a measurement system in such a way that the measurement error, is it okay? That means the deviation from the actual measurement error is at the minimum level, at least minimum level, if not eliminated altogether. The ideal situation is that I have created an inspection system, measurement systems in such a way that there is no measurement error, but that is your goal. But obviously achieving that condition is very difficult. Okay, maybe you will be heading towards that, but make sure at this point in time that the measurement error is held at the minimum level. So if the measurement error, if not under control, what is its implication? It may lead to incorrect and misleading conclusion about the process capability. Okay. Now there are certain other the remarks I like to make. Measurement systems capability analysis is a prerequisite for process capability analysis. Is it okay? So first you concentrate on the measurement system, and then you start using the measurements. If you say that the measurement system is highly capable, you have tested the measurement systems from several relevant perspectives, and then you say, now I will go for process capability analysis, and while I carry out process capability analysis, I will collect data, and while I will collect data, I will be using a capable inspection systems or measurement systems. So in this analysis, the measurement error is first quantified. This is to be quantified, and then the sources and causes of errors are identified. Is it okay? And what we believe in, that the measurement error is a function of time primarily. That means as the measuring instrument becoming say older and older, that means getting aged, so it is most likely that the measurement error will be more. So first you estimate the measurement error, you identify the sources and causes of errors, and then you take remedial and preventive measures. Is it okay? Or corrective measures you take. Now one important term you need to explain at this stage, that is what is gauge variability and how the gauge variability is related to the total variability. Is it okay? You are getting several sorts of for different parts you are getting, and suppose you start measuring the part, that means related to a part, what is that quality characteristics. So this quality characteristic, the value you are getting for the different units of the part. So you need to measure the variability of the measurements, So how do you do that? You need to carry out certain experimentation and certain approaches you have to follow, you have to use. The total variability, first you have to define the total variability. Total variability is due to the variability in product, that is most important in fact, variability in the product itself. Is it okay? Because in reality what you are trying to do, that means you are producing certain dimension. Is it okay? Now this dimension you are producing the physically. So that is basically the variability in product, as well as due to variability in the measurement error. Is it okay? There is one dimension which actually it is there physically. Now you get an idea, you are measuring that while you measure that dimension. Is it okay? You use the measurement measurement systems or measuring instruments. While you use the measuring instrument, again there could be some error. Is it okay? Due to measurement systems. Is it okay? So two kinds of so the variability you have in the total variability. So the notation is, how do you measure variability? Obviously you know that is basically a measure of dispersion, and the best possible measure of dispersion is variance. So the total variance is equated with the product variance. Is it okay? And the gauge variance. Gauge means the measuring instrument. Is it okay? Sometimes this is referred to as the measurement error. Is it okay? So measurement error. So so the gauge variability is also known as the measurement error. Now here is an example. Let me make this concept very clear to you. Suppose for measuring the gauge variability, what you need to do, or the measurement error, you have to collect data in a specific manner. So here you need to consider a number of parts, say 20 parts I will collect. Okay. So 1 to m. M could be 20, it could be 25, a reasonable number, say 30 such. Okay, you have collected. Now what you try to do, that means you use a measuring instrument, you identify the corresponding quality characteristics, say length or the width or the diameter, which is related to a particular diameter, or a particular, say the length, that is your quality characteristics of interest. What do you try to do? You use the measuring instrument and you measure the same dimension twice. And what we are assuming, that these two dimensions are independent. That means no way you are influenced by the previous dimensions. Is it okay? So independent. So the part number 1 you measure twice. In the first you get 21, whatever may be the units of measurement. The next time when you measure with the same instrument, you get a value of 20. Is it clear? So what we are assuming, that while you measure for the second time, you are not influenced by the way you measure for the first time. Is it okay? So the second time measurement is no way influenced by the first time measurement. So what is x bar values? That means two values, the 21 plus 20, 20.5. What is the range? That means there is a sample size is 2. Okay, two values you have obtained, and what the range is just 1. That means 21 minus 20. So similarly, for all other parts, you get the value. Is it okay? In this manner, like for the third part, first time you measure, it is 27 shown. The second time is also 27. Obviously, the range will be 0 and the mean will be 27. So this the data are collected in this manner. You create such a table. Okay. What is your objective? Objective is, I am going to measure the gauge variability. Then from this, what do you try to do? That means the sigma gauge, that is R bar by D2. It's clear? So the R bar, that means several R values you have considered, several R values you have considered. Now you get the value of R bar divided by D2. these expressions already we have derived, okay, when we discussed say R and X bar control chart. So the corresponding values you get, and this d2 is a function of say the sample size, and here the sample size is 2. Is it okay? N equals to 2. Please note that n equals to 2, and you refer to the control chart factor table. So against n equals to 2, you get the value of d2 as 1.128. So it is 0.887. Now, as you know that we say that the capability, that means the NTL, natural tolerance limit, we calculate. Is it okay? And that is indicative of say the capability. Is it okay? So here the gauge capability is referred to as, so okay, 3K into sigma. Are you getting my point? So already you have computed sigma gauge, and this is 6 times. That means what we are assuming, that is the 3 sigma on one side, that is UNTL, and on the other side, that is minus 3 sigma from the process the mean, that is the mean value, that is LNTL, lower natural tolerance limit. So 6 into sigma gauge is an estimate of the gauge capability. It's clear? So what is this value? The value is here 0.887 you have already obtained. Just I am giving an example. So 6 into 0.887, that is 5.32. So what do you conclude? The conclusion is that individual measurements can be expected to vary as much as plus minus 3 sigma gauge. Is it okay? So the total area is UNTL minus LNTL. Is it okay? Now what is the variation? Variation is across the mean. Is it okay? So the vary plus minus 3 sigma gauge from the mean, that means that is the area. You specify the area due to gauge error. So these simple calculations we do, but just make a note that you have to collect data. That means some sort of experimentations you have to do, and you have to collect data as per the given format of the table. Now in industries or in manufacturing organizations at the shop floor, what you find that many a time when you refer to these particular concepts, a measurement error, they might refer to one particular ratio, that is called P by T ratio. P stands for precision and T stands for the tolerance. So precision to tolerance ratio. Now what is this precision to tolerance ratio? Now many a time you will find at many shop floors, at manufacturing plants, you will find that it is considered to be a relevant measure, and they conclude about the gauge variability or measurement error by referring to the value of the P&T ratio. Is it okay? So first let me explain what is this P&T ratio. That means the precision, that means the repeatability. That is very, very important one aspect. Sometimes the precision is referred to as a repeatability. Okay, so that is just one dimensions of the precision, right? So this is referred to as a 6 into sigma gauge. Already we have computed, and then it is what we are trying to do. That means you are trying to measure a quality characteristics. Is it okay? So you refer to that particular quality characteristics. Suppose it is a double specification limit case. That means you have USL, you have also LSL for the given quality characteristics. Suppose this could be say 60, this could be say 10. So this is 60 minus 10, that is 50. So USL and LSL, these two values are prescribed by the designers. They are known, they are assumed to be constant for the time being. So you can immediately calculate P and T. Now there is some thumb rule existing, or they are referring to some thumb rule as far as P and T ratio is concerned. They say that that the P and T P by T ratio must be less than 0.1. That means the 10% of that. That means this is the total the variability I am allowing as far as gauge is concerned. Now you check whether it is the 10% of the the required spread, that means allowed spread. This is basically the allowed spread, and this is basically the actual spread. Is it okay? 6 into sigma, and assuming normality, obviously. So what is that proportion? If the proportion is less than or equals to 10%, they say is fine. Means the measurement error or the gauge variability is acceptable. Is it okay? Now, when you refer to such data and you go for data analysis, there is a possibility that instead of referring to P by T ratio, there could be better measures. So that I am going to discuss, and definitely you will be calculating P by T ratio, but sometimes you may have misleading conclusions. So a better approach is always prescribed. Now, what you try to do actually, from the given set of data, if you refer to this particular table, what you will find that suppose there are say 30 say the parts you are dealing with, initial table, and each part is to be measured twice. So you have essentially, suppose there are 30 parts, that means you will be getting some 60 such measurements. So what you try to do, that means first you calculate the total, the variance. The notation is sigma square total. That is basically the sample variance. So you know how to compute the sample variance from the given data set. Is it okay? So you compute this. Now what you try to do, you have so if this is known, obviously now you can calculate the sigma square product, the sigma square product. Is it okay? That means the variance of due to product, that is sigma square total minus sigma square total minus sigma square gauge. It's not total, it should be gauge. Sigma square total minus sigma square gauge. Is it okay? So it is 10.05. Suppose this is the data you have got and you have calculated as 10.05, that is sigma square total. Suppose for a given case, just I am setting one example, and this is suppose 0.79, that means it is 9.26. So obviously the sigma square product, that means due to the product you have this variance, that is 3.04. okay. Now what you try to do, that means you calculate that how much is the sigma gauge in with respect to sigma product. That means what is the proportion of the sigma gauge, is it okay, proportion with respect to the sigma product, that is the proportion. Okay. So sigma gauge by sigma product you calculate. So it is 0.887 divided by 3.04. That means it is 29.2%. That means one part of the variability is due to the product, okay, and one part of the variability is due to the measuring instrument. Now you check that what is the error proportion, okay, due to the gauge or the measuring instruments vis-a-vis the product variance. Is it okay? So this may be treated as a better measure than P&T ratio. So that's the point I have made, that is, this is considered a better measure of gauge capability than the conventional P/T ratios. But again, you may be referring to several case studies. That means under certain conditions maybe the P/T ratio may be recommended and you might have taken the best decision. But in other situations, maybe the P/T ratio may not be valid. But first you have to prove that it is not valid, and then if it is not valid, then you opt for the alternative ratio, that is sigma gauge by sigma product. Is it okay? So this is an important consideration. Now then, how do you explain the measurement error? So first what you do, that means the total variability is equated with the variability due to the product and variability due to the measuring instrument. So that is referred to as measurement error. Now what you need to do, that means further you need to study this measurement error. So now if you have this measurement error or the gauge variability, that is sigma square measurement error, that is sigma square gauge, that's the notation we have been using. Now there are two aspects. That means this error may be due to the repeatability or maybe reproducibility. Now what is the repeatability? That means you'll be using the measuring instrument, okay, under the same conditions. You will be taking measurements a number of times. So you are not changing the conditions or the constants. So that is repeatability. Is it okay? That is the repeatability. Now the second aspect is, suppose you use a measuring instrument, but you change the conditions. You have changed the conditions, and in which a particular part is getting measured. So that is basically when you start this measurement, the data under different conditions. So again you may observe there is a variability. So this variability is referred to as the sigma square reproducibility. Is it okay? So these two aspects to be looked into, right? So for looking into these two aspects, what you need to do, that means again you have to collect data in a different form. So here I am just explaining this particular table. Like say you are dealing with say 30 parts, m number of parts. Is it okay? Now you have engaged 3 operators. That means this is one condition, this is the second condition, this is the third condition. That means what we believe in, that means the concept of individual difference. That means this is the data operator 1 has generated, okay, same say by using a measuring instrument, and he measures each part twice or thrice. You said twice. So you have this data set. Is it okay? You calculate, okay, say corresponding x bar and r individual one. So you have for the first operator x1 double bar, mean of the means, that is 20.30. This is just an example. And R1 bar, that means R1 stands for actually for the first operator. So this is 1.00. It's clear? That means you have all these values, you add them and you take this average. That is basically R1 bar. Similarly, you ask the second person to measure the same parts twice, okay, with the same measuring instruments. Is it clear? So what you will be getting a different set of data. It is least likely that the same data set will be repeated by the second person or the third person. It will never happen, because the way I as an operator, okay, using the instrument, right, it has a bearing on the the data which you get, is the quality of data which you get. The other persons, he or she will be using the same instrument in a different manner. This is unavoidable. It's a noise factors. These unavoidable noise factors or uncontrollable noise factors. Unit to unit variation, uncontrollable noise factors. So the operator to operator variation, that is a must. So these variation to be looked into, and when you look into this variation, this is referred to as the reproducibility. So the level of reproducibility is this one, and when you engage the third person and ask him or her to measure these parts twice, so he or she produces this sort of data set. So obviously they just cannot be the same. So the level of difference is essentially the level of reproducibility, okay, that we are going to measure. So for the second set of data you have x2 bar and this is r2 bar. Similarly for the third set of data you have x3 double bar as well as r3 bar. Now what you do some calculations. That means as far as repeatability is concerned, you refer to the range data. Is it okay? You have r1 bar from the first operator, r2 bar from the second operator, r3 bar from the third operator. So you have 3 operators, okay. So this the value is r double bar. That means the mean of all these 3 ranges, that is 1.15. So what is sigma repeatability? that is R double bar by D2. The same formula we have been using, that is 1.15 divided by 1.128, and this is 1.128 when n equals to 2. It's clear, because the range calculation is possible only when the minimum 2 number of data points are available. Is it okay? So this is 1.02, and the next for computing reproducibility, what you need to know, that means you have 3 values, x1 double bar, x2 double bar, x3 double bar. Now out of these 3 values, one will be the maximum one and one will be the minimum one. So if you subtract the minimum one from the maximum one, you get the range value, is it okay, related to x. And so how do you define sigma reproducibility? That means R subscript x double bar divided by D2. Now this D2 is actually for n equals to 3, because 3 values you have taken, so not 2. So it is 0.20, suppose just an example, divided by 1.693. So this value you can read from the control chart factor table. So that is 0.12. So now what is the sigma 2 square gauge? That means 1.02 square plus 1.12, that means 1.0548. So sigma gauge is 1.03. It's clear? So now you can calculate PNT ratio. You will find that means it is 6 into sigma gauge, that is 6 into 1.03. The PNT ratio can be recalculated to verify if it is within 0.10, 0.1 or not. That means the 10%. Is it clear? So now what we have done, that means sigma square total we have calculated, and one important the component in sigma square total is sigma square gauge. So that is the first level calculations we did. At the second level, now the sigma square gauge is equated with sigma square repeatability as well as sigma square reproducibility. So that's why we are engaging, say other persons or other conditions. Is it okay? And then you get the data set, you calculate both, that means sigma square repeatability as well as sigma square say reproducibility. When you add them, you get sigma square gauge, and then you check that to what extent whether the p by t ratio, okay, the value of p by t ratio remains same or not. Later on, we'll be taking up examples of the numerical examples, and obviously we'll be using these formulations for solving the numerical problems. Okay, so I conclude the lecture sessions on process capability analysis. We have dealt with several important the issues related to process capability analysis. Is it okay? Including the most important aspect, that is the measurement error. And we believe in the philosophy of philosophy of the quality is as good as the measuring instruments. Is it okay? So the process capability we have dealt with, as well as the measurement systems capability. Sometimes the measurement systems capability is referred also as the inspection systems capability. Okay, so I conclude the session.